Hello everyone, welcome back to finite-element method. In this video, we are going to look at how we can solve this plane trusses problem using finite elements. Where in this video, we are trying to solve this problem in such a way that we are going to straight away generating or producing the system of linear equations, what we call it as a reduced system of linear equations, instead of the full system of linear equations of the whole plane trusses system here. The way we solve this problem will be slightly different to the one that we have in the lecturer's notes. Alright, now we have a plane trusses problem, which is our truss system is or our truss structure is the one that is drawn using the black line here, which is representing our plane trusses structures. And these structures, as we can see here, has made of 1, 2, 3, 4 elements, and this structure is simply supported at nodes number 1, nodes number 2, and nodes number 3, while the node number 3 is left hanging. And as you can see as well, at nodes number 2, there is an external load applied horizontally in the x direction with 20,000 pounds. And at nodes number 3 here, we have external load applied vertically pointing downward at 25,000 pounds. Given that the structure here has the dimensions 40-inch length and 30-inch height. Given as well the modulus of elasticity of this structure, which is 29.5 times to 10 power of 6 pound per square inch, and the whole element here has the same the cross-sectional area of 1 inch square. So our problem here, we are asked to determine one, the displacement at nodes number 2 at this particular point there, and then the nodes number 3 as well. And number 2, we are asked to determine a stress in element number 3, which is in these particular elements. Now let we consider the boundary conditions of our structures. At nodes number 1 and nodes number 4, the structures is supported by pin fixed boundary conditions, and at nodes number 2 is supported by this pin roller boundary conditions. So now let's look at this our first boundary condition, which is pin fix. So the behavior of a pin fix boundary condition is actually tell us that this particular or any particular structure that attached to the pin fix is actually freely to rotate to the left and right. But at this particular point here, due to the fixed boundary condition, then there will be no displacement to the left and to the right, and also there will be no displacement to the in the vertical direction due to the fixed boundary conditions. So there will be no vertical and no horizontal displacement. But for the pin roller boundary conditions, it behaves similar to the pin fixed boundary conditions, where the elements or structure is freely to move to the left and right. But at this particular points, due to the roller that positions in these directions, then it actually allows these particular points to move to the left and to the right. But due to the fixed boundary condition that we have, then there will be no vertical displacements or movements in the y direction. So due to the roller, we only have the horizontal displacements. But in the plane trusses problems, the rotations of the element is not considered. The next step in solving the plane trusses problem using finite-element method is by establish the element connectivity, which is, as we can see here in these tables, each element is shown how each element is connected between each nodal points, and we can use this element connectivity to draw the directions of the connectivity for each element. For example, for the element number 1, it is connected from 1 to 2. Then we can use this information to draw the directions of the connectivity for element number 1, which is it's starting from nodes number 1 towards the nodes number 2. For the element number 2, it is connected from 3 to 2, so we can draw the direction as well. For element number 3, 3 to 1, and for the element number 4, from 4 to 3. For finding the angle theta, we will use the horizontal line as our reference line for generating or finding the angles. So, for example, if we dealing with element number 1 where it is connected from 1 to 2, then it means here we will use our nodes number 1 as the reference, and then we take this angle. We can say that for 1 to 2, the angle will be equal to 0 degrees, or we can take this equal to 360 degrees. So the angle is obtained by taking it in always in anti-clockwise directions. So, for example, if our element is connected from 2 to 1, then the angle for our element here will be considered by taking nodes number 2 as our reference, and then we take this angle by making the anti-clockwise from our horizontal or reference lines until it meets these elements number 1 here. So as we can see here, for this kind of element connectivity, the angle will be 180 degrees. So it's slightly different in terms of the element connectivity, whether this element is connected from 1 to 2 or 2 to 1. Then similar apply to others element as well. Then we have to build a similar approach in order to obtain their angles. So when we have developed this angle, then we can write or fill our table here so that we can have table as shown here. If we can remember, the element stiffness metric for each element or truss element written in global coordinate system can be obtained by filling up these informations. Thus, before we fill up this information, then it is important to first go back and look at the boundary conditions of our systems. So we come back to our system here or structure here. Then it is very good to label the all the degrees of freedom that we have on our structure here. So at element number 1, actually we can write Q1 and Q2. If we can remember, we will follow these sign conventions for the displacement. So in the x direction we have 2i minus 1, and in the y direction we have 2qi. So at nodes number 1 we have q1, q2, we have q3 and q4, q5 and q6, q7 and q8. So this is all the degrees of freedom that we have on our whole structure here. And then looking at the boundary conditions, as we discussed just now, at nodes number 1, it is supported by pin fixed type of boundary condition. Then we can see that there will be no displacement in the x and in the y directions at nodes number 1. Similar at nodes number 4 as well. So we can do something like this. For the nodes number 2 here, we have a pin roller. So here maybe we have some displacement due to the roller positions, and then there will be zero displacement in the vertical directions. At the nodes number 3, there is free joint here, and we may have some deformation both in the x and y directions. And using this information where we have q1 equal to q2 equal to q4 equal to q7 and equal to q8 equal to 0, while q3, the only displacement that we may need to obtain from our calculations later. The next step in preparing our system of linear equation is first to solve for the element stiffness metric, which is the element stiffness metric for each element is given by these equations. So we have to prepare this K metric for each element, for element number 1, for element number 2, element number 3, and for the element number 4, which this equation, as we see here, is already written in the global coordinate systems. Now is how we can prepare this element stiffness metric correctly. So considering that we have element number 1, which is spanning from node 1 and node 2, so this is our element number 1, and our element is connected from 1 to 2, and if we draw the deformation or displacement at each another point, then we will have q1, q2, q3, and q4. Looking at these degrees of freedom and the directions of the element connectivity, then we can write the address next to our matrix by following the index that we have for the deformations, and by considering the element connectivity as a direction as well. So for the element that is connected from 1 to 2, then we will start our index here by writing the address to our matrix here. 1, 2 refers to 1 and 2 here, and followed by 3 and 4, which is to follow the directions of the element connectivity. And at the side as well, we can write it 1, 2, 3, and 4. For the element number 2, which is connected from nodes number 3 to nodes number 2. This is our element number 2. Then similarly, we can draw this the degrees of freedom. So we have q3, q4, q5, q6. But in terms of the directions of element connectivity, it is connected from 3 to 2. So the way we write the address to our matrix will start from 5, 6, 3, and 4. So I will write here 5, 6, 3, and 4, 5, 6, 3, and 4. And similarly, apply to the element number 3 and to the element number 4. So we have to write the address according to its element connectivities for each element. Once we have this done, now what we can do is to look at the boundary conditions, where for all the displacement that equal to 0, or where the another point that has no displacement, then we actually can eliminate the row and columns where we have no displacement. For example, we know that Q1, Q2, Q4, 7 and 8 equal to 0. Then we can eliminate the rows 1 and 2 and column 1 and 2 due to this boundary condition, which is equal to 0. So we apply to all elements for this element stiffness matrix on the Q4 is equal to 0. Then we eliminate row and column number 4 for the element number 5. So we eliminate the row and column number 1 and 2 due to these pin fixed boundary conditions. And then for this particular element number 4, we can eliminate the row and column number 7 and 8 due to the pin fixed boundary condition as well. So by eliminating the inactive, so this is what we call it as inactive boundary conditions. So we can actually write our element stiffness matrix in a reduced format. That means from a 4x4 into the lower size of the matrix, depending on the boundary conditions that we consider. By having our element stiffness matrix for each element has been prepared as shown here, actually it will allow us to write our element stiffness matrix for the whole system, which is initially our global K matrix will have 8 by 8 in terms of its size. But now after we apply the boundary conditions, then actually it allowed us to write our element stiffness matrix for the whole system, which is reduced into 3 by 3 in terms of its size. So I would recommend you to simplify your equations by applying the boundary conditions at this stage, so that you can prepare the element stiffness matrix in the reduced formats, which is I can write here our K matrix. Instead of having 8 by 8, now we can only write our K matrix in the global coordinate system for the whole structure, that will having the index that refers to the displacement 3, 5 and 6. So our system will have only 3 by 3 in terms of its size. So by having this reduced format, it will reduce a lot of the calculation process for solving the system of a linear equation. So if we can remember, the final equation that we have to prepare will be in the form of the system of linear equations, which is will be written as KQ equal to F, which is all of these written in the global coordinate systems and representing the whole structures, where since we have 4 elements, then the K global will be contributed from K1, K2, K3 and K4, which is we have to add all of these element stiffness metric for each element to make a global systems. So after we assemble the K for each element, then we found that our element stiffness metric for the whole system, after we substitute the value into all the variables, then we will found that our global element stiffness metric and then Q matrix will be Q3, Q5 and Q6. For preparing the force vector, then it is better to come back to our structures and evaluate the external forces that apply to these structures. And looking to this problem, we only have two external load apply, which is 2,000 pounds applied at node number 2 in the x direction, which is equivalent to F3. And then we have vertical force which apply at nodes number 3 in the vertical directions, in the downward directions, which is we can call it as F6. There is no external force apply in the horizontal directions as node number 3. Then we can say that F5 equal to 0 in this case. So we have all of this done, then we can transfer this value into our system of linear equations. So the negative sign for F3 here actually refers to the negative direction of force as compared to the positive y directions. Our system of linear equation now is ready to be solved for the unknowns displacement Q3, Q5 and Q6. And solve using calculator gives the displacement Q3, Q5 and Q6 are equal to 27.12, 5.65 and negative 22.25, and all of this multiplied by 10 to the power of negative 3 inch. So once we have obtained the displacement Q3, Q5 and Q6, then we can draw the deformed structure as shown below.